All right, everyone. Hello, welcome. We are going to keep moving forward with our video lecture series. Today, we are going to be talking about the Mass-Energy Equivalence. This is a fancy way of saying that we are going to be talking about nuclear physics. All right, so this is another step into that modern realm of physics. Okay, so first question. When we're talking about nuclear physics or nuclear reactions, nuclear power, any of these words, a lot of people kind of brush over what is the most obvious thing. If I said, what is a nuclear reaction, right? A lot of people would sit there and say, an explosion, that's something to do with uranium. They're not really sure. Which is here is where it's really useful to just break the word down, right? We're talking about nuclear reactions. Well, if we're talking about nuclear reactions, the question is, what part of the atom are we talking about? And a nuclear reaction involves the nucleus. That's it, okay? All nuclear reactions are reactions that involve the nucleus of an atom. Now, if you remember, the nucleus is incredibly small. It makes up a very, very, very small percentage of the volume of an atom, but it makes up the vast majority of the mass of the atom. Okay? More importantly is the location. The nucleus is in the middle of the atom. Most everything we've talked about so far has been about the electrons. They're small, they're on the outside of the atom, they can very easily jump from one atom to another, right? When they spin, they create magnetism. When they jump from one atom to another, they create electricity. But today we're going to be talking about what happens when we mess with the nucleus of an atom. Okay? So, nuclear reactions. All right, a nuclear reaction, number one, causes the nucleus, I get 2 for 1. It causes the nucleus of an atom to change. This is the most important aspect. Okay, I've been saying this a lot. What does that actually mean to change the nucleus? All right, the nucleus of an atom contains positive protons and neutral neutrons. Okay? The number of protons in an atom determines what it is. All right? If an atom has 1 proton, it's hydrogen. If it has 2 protons, it's helium. If it has 3 protons, it's now lithium. Okay? When you change the number of protons, you change what a substance is. That's the difference between oxygen and carbon, is the number of protons between the two. Okay? The second thing about nuclear reactions, which you probably already knew, is that they produce massive amounts of energy, huge amounts of energy, all right? This is why atom bombs are so destructive. This is why nuclear power plants are super efficient. We'll get into that in a little bit. The last thing here is you have to realize that whenever you're talking about nuclear reactions, you are fundamentally, okay, you are in itself changing what an atom is. If an atom undergoes a nuclear reaction, it turns into something else, okay, which is kind of crazy to think about, okay? And what this means is that through these nuclear reactions, we can turn atom A into atom B, all right? Okay, so let's talk about the 2 types of nuclear reactions, okay? The first type is called fusion, all right? And fusion is exactly what it sounds like. When you hear the word fusion, if you think about 2 things coming together, fusing together, you would be correct, all right? In fusion, what happens is you have 2 very small atoms, the nuclei specifically, and they come together to form one bigger, heavier atom, okay? Fusion is 2 things, 2 small things coming together to make one big thing. The thing about fusion is that it requires an enormous, a massively insane amount of heat and pressure in order for this to take place, all right? And when I mean a lot of heat, I mean like million degrees of heat and, thousands of areas of pressure, okay? Usually, it requires a lot of energy as well, and usually the atoms that are involved in fusion are very, very small. And the smallest atom there is is hydrogen. Okay, sometimes helium is used, but those are the two smallest atoms. All right. The thing about fusion is that it requires so much heat and so much pressure. Okay, atmospheres of pressure. Thank you, forgot about that one. Requires so many degrees of heat and so many atmospheres of pressure. Okay, that it doesn't take place anywhere on Earth. In fact, the only place that fusion happens in the entire universe is inside of stars like our sun. Okay, and the only place where you can have enough pressure and heat to bring two atoms together is in the inside of a star, and that's because there are millions of degrees in Fahrenheit and thousands of atmospheres of pressure. Okay, so this is fusion. Okay, again, I would recommend writing this down. You have two small nuclei, two small atoms come together to form a bigger atom. All right. It requires an insane amount of energy, it requires an insane amount of heat and pressure. It usually involves hydrogen, and the only place that we really are going to consider it happening right now is inside of suns and our sun and the stars. All right, so if we have fusion, okay, here we see two hydrogens coming together, and these two hydrogens, they both have one proton. When they come together, they form helium, which is a slightly bigger atom. It's the one that makes your voice all squeaky when you suck in a balloon, right? It also produces a massive amount of energy, all right? We'll get to that in a second. Number two, if we have fusion, we also have fission, okay? If fusing two things together means combining them, a fissure or fission is when you split them apart. So fission is what happens when you take a really big atom, okay, and you chop it in half into two smaller atoms, which is what we are seeing in this picture right here, okay? All right, so you take a large, unstable nucleus, all right? The reason we say that this nucleus is unstable is because it already wants to split in half. Most atoms don't want to split in half. Most atoms want to stay whole. All the atoms we usually talk about, your carbons and hydrogens, heliums, oxygens, nitrogens, gold, iron, all that stuff, those atoms want to stay together. They don't want to split up. But there are a couple of elements that naturally like to break down, okay? And when an atom likes to break down, we say that it's radioactive, okay? So if you can think of things that you know as radioactive, okay, you would think of things such as uranium and plutonium. These are what you need in order to have a nuclear reaction, a fission reaction, okay? And this is why you'll hear about these things when people are talking about making nuclear weapons or running a nuclear power plant, all right? And the reason that these are unstable is because uranium and plutonium, as they just exist, their protons slowly fall off, okay? They do what's called radioactive decay, okay? As those protons fall off, the uranium slowly becomes different elements, which is crazy to think about, but that's what's happening, okay? Fission, okay, as you can see here, you start off with one big chunk of uranium, okay? A neutron comes and smacks into it and poof, splits it into two smaller atoms, okay? This is what we use in our nuclear reactors, okay? As I'm sure anybody who's tried to build something before understands, it is much easier to break something in half than it is to create something, okay? Fusion, the creation of a new atom, is very difficult, okay? Fission, slightly easier. So, fission is what we use in our nuclear reactions here on Earth. Nuclear power plants, nuclear bombs, things like that use fission, all right? It creates a ton of energy for certain, but it does not create as much energy as fusion, all right? So fusion is much more difficult, requires much more energy, and only really takes place inside of stars like our sun. Fission requires less energy, it's a little bit easier, and we can do it in nuclear reactions. The problem with fission is that it makes dangerous waste, okay? Fission, because you're cracking things in half, because you're breaking things, there are leftover products, and those leftover products are radioactive waste, which is dangerous. Fusion does not create radioactive waste, okay, which is another difference between the two. And again, if you want to pause the video and write that down, that could be helpful when you're doing your DOL. All right, so let's look at a picture of the two. So again, here is nuclear fission. The simplest way to think about nuclear fission is you start off with an unstable element like uranium. Okay, remember, uranium does not like to stay together. Its nucleus wants to split apart. And if you add a little catalyst, something to speed this up, like a neutron, if you can hit an atom of uranium with neutron, it will split into two lighter elements, okay? It'll split into these smaller elements. When it does that, it releases 3 more neutrons, which smack into 3 more uranium elements and split those in half. And it starts what's called a chain reaction. This is what happens inside of nuclear reactors. Uranium is zapped with neutrons, splits in half. That releases more neutrons, which hit more uranium atoms, causing them to split in half to create more. It's like a pyramid scheme, okay? How does this used inside of a nuclear power plant? All right, well, it's actually pretty simple. If you think back to when we talked about generators, the way that it works is you have here is your reactor vessel. All right, so in here you have your nuclear reactions, okay? These nuclear reactions, in here you have uranium, okay? And that uranium is being zapped with neutrons splitting in half, releasing tons of heat energy, okay? That heat energy goes through a tube and into a big vat of water, okay? And when you hit water with a lot of energy, it boils and it creates steam. That steam goes up through another pipe and it hits a turbine, right? And if you remember, a turbine is just a big fan that's able to spin around, okay? That turbine spins around and that turbine is connected to a generator. Inside that generator is a magnet, okay? That magnet spins around inside of a big coil, okay? And if you remember, whenever you spin a magnet around inside of a coil, you create electricity. Voila! So really, a nuclear reactor is very similar to a hydroelectric dam or a windmill or even a coal burning plant where all you're doing is you're using that energy to spin a turbine that's connected to a generator, okay? In theory, nuclear reactors are extremely efficient and they create almost no pollution. They're considered extraordinarily clean sources of energy, except for the fact that they produce radioactive waste. The problem with radioactive waste is that we don't really have a way to deal with it. We don't have a way to get rid of it. And that is one of the bigger problems with nuclear reactors. Obviously, the other problem, if you've ever heard of Chernobyl or 3 Mile Isle or any of those things, is that if something goes wrong inside of the nuclear reactor, things go really wrong. And you can release insane amounts of radiation into the surrounding areas. If you remember Fukushima, that's what happened. Chernobyl, that's what happened, okay? So the idea when you're thinking about nuclear energy is that it's really efficient, it's really clean, except when it's not. And when it's not, it's super, super, super dangerous, okay? All right, so again, here we start off with a big old chunk of uranium. We hit it with a neutron, it splits, and you have 2 smaller atoms and 3 more neutrons ready to go and smack 3 more uranium atoms. Fission. Fission splits, fusion comes together. Now, how does this create energy? Okay, maybe that's what you've been thinking. You're like, why does splitting an atom in half or fusing 2 atoms together create energy? So let me check, make sure I'm still recording. All right. Well, here's how. Whenever you take a big atom and split it into 2 small parts, okay, that original atom, okay, this one large atom becomes 2 smaller atoms. When that happens, the mass of the products, meaning what you produced, is less than the mass of the reactants, meaning the atom you started with, okay? What does that mean? That means that the atom that you started off with is bigger than the 2 atoms that you made. Seems kind of weird, right? we learned that we can never create or destroy energy. And if we can't create or destroy energy, when you take a big atom and split it into two, you lose some mass. But we can never lose mass, right? And it has to turn into something. And what that turns into is pure energy, okay? This is because of Einstein. We'll get there in a second, okay? Nuclear reactions. You lose a little bit of mass, and that mass becomes pure energy. Same thing in fusion, what happens inside of our sun, okay, or any star for that matter. You start off with two hydrogen atoms, okay, and they come together to form one helium atom, right? Look, we have one proton, one electron, one electron. We add them up, we squish them together with tons of pressure and heat, and they become a helium atom, which has two protons and two electrons, all right? The same thing happens. The mass of these two hydrogen atoms is greater than the mass of one helium atom. So again, we lose some mass in this reaction, but the mass is not lost, it's just converted into pure energy because of Einstein, okay? So this idea of mass becoming energy and energy becoming mass is at the fundamental, this is the fabric of the universe right here, okay? And this is one of the bigger discoveries of the last 150 years, all right? And if you want to watch any videos about Chernobyl or what happens when a nuclear reactor explodes, I've linked them here. Okay, the links are right up here. Have at, watch them. They are pretty intense, but really interesting. But the big part about today, okay, on top of how nuclear reactions work, is probably the most famous equation of all time. I'm sure you've heard it at some point. It's E equals mc squared. I'm sure you've seen it written somewhere. It's Albert Einstein came up with this, okay? But let's talk about what it actually means. All right, so E equals mc squared. What does this mean? This is called the Mass-Energy Equivalence, okay? All right, so what this says is that we have E, which if you want to guess, E stands for energy, okay? It's how much energy is in a system. M stands for the mass of the system, okay? If you forgot, I'll write this in. Energy is always measured in joules, and mass is always measured in kilograms, okay? And the last thing we have is c squared. Well, if you think back, okay, to about a month and a half ago, you'll remember that c is the speed of light, okay? The speed of light is 3 times 10 to the 8th meters per second squared. It's how fast all light travels. And what Einstein realized is that if you take mass, okay, like that little tiny atom, okay, and if you can convert that mass into pure energy, it releases an enormous amount of energy, okay? Mass can be converted into energy, and energy can be converted into mass, okay? They're kind of one and the same. So, what does this mean for us? Well, we know that c is equal to 3 times 10 to the 8th meters per second squared. This number, if you remember, is 300 million. 3 times 10 to the 8th, which is 3 followed by 8 zeros. That's a large number. But c squared is not 300 million. C squared is 300 million times 300 million, which gives us this number. It's a 9 followed by 16 zeros. 1, 2, 3, 4, 5, 6. 16, which gives us boom, 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 boom. This is, let's see, we have thousands, millions, billions, trillions. This is 90 quadrillion is that number. It's a number so big that you probably rarely even say it, okay? So the reason that nuclear reactions are so strong, okay, is because you're taking an atom, let's say fission, you take an atom, you split it apart, okay, and a small little tiny fraction of that atom turns into energy. Even though that amount of mass is so small, you're multiplying that mass by 90 quadrillion, which means you're releasing an insanely large amount of energy, okay? E equals mc squared tells us that a small amount of mass turns into a lot of energy, m into E, okay? All right, and ignore this. If you make it disappear, it's not disappearing, okay? It's being converted. All right, so let's work on a practice problem. So there are going to be a couple math problems this week. Don't freak out. They're not difficult. I'll show you how to answer them, okay? What is the equivalent energy of 1 kilogram of matter? Okay, meaning if you take 1 kilogram of matter, how many joules of energy do you get? Well, we have E equals m times c squared, okay? E is what we're looking for, okay? That's our question mark. Our mass is 1 kilogram, and C equals 3 times 10 to the 8th meters per second, okay? All we do is plug our numbers in. E is I don't know, M is 1 kilogram, C is 3 times 10 to the 8th squared. Do not forget to square C. That's the biggest crux of all of this, okay? So we go through this. This gives us 1 kilogram times 9 times 10 to the 16th. 9 times 10 to the 16th is 3 times 10 to the 8th squared. And that gives us 9 times 10 to the 16th joules, because 1 times anything is itself. All right? I understand you might be scratching your head. I can't see your faces, so I'm going to go over a few more of these. All right? Let's look at, okay, a large unstable nucleus of element A with a mass of 3 grams falls apart, producing 1.5 grams of element B and 8 grams of element A. How much energy was created? Okay? Let's go through this. Number 1, we need to figure out how much mass was lost. So we started with 3 grams, okay, of an original substance. So our original mass is 3 grams. Okay? We ended, okay, with 1.5 grams of element B and 0.8 grams of element C. We want to know how much was lost. Okay, what's the remainder here? Let's call that X. Okay? Well, 1.5 plus 0.8 gives me 2.3 plus X. So what plus 2.3 equals 3? Well, this is addition. So you do the opposite. Okay? 2.3 minus 2.3 is 0, and 3 minus 2.3 gives us X is equal to 0.7 grams. Okay? So here, I know that the amount of matter that was lost is equal to 0.7 grams. Okay? We look at this right here. All right? So now what we do is we have to use E equals mc squared to see how much energy we get from 0.7 grams. Okay? So we have E equals m times c squared. Okay? Means the energy is going to be equal to our mass, and this one's a little tricky because I use grams. You have to convert it to kilograms. So 0.7 grams is 0.1237 kilograms. Don't worry about that conversion. Times 3 times 10 to the 8th squared. Okay? So we know that 3 times 10 to the 8th squared is equal to 9 times 10 to the 16th. Okay? Times 0.0007. Okay? So all you have to do is multiply 9 times 10 to the 16th by 0.0007. And you're sitting there and you're like, I don't have a calculator, Mr. Norris. Watch this. We go back to our Google page and we look up calculator. Well, let me bring it over here. All right, so here is our calculator. And using this Google calculator, which I found by Googling the word calculator, you can do all of the math you need. So here, I'm going to type in 0.0007, okay? Okay, And we're going to multiply that times parentheses, and we type in 9 times 10 to the 16th the exact same way as we did before. Okay? We type that in as 9, and you see where it says EXP? That's your EE button. E, and then you just put the exponent, 16. Close parentheses, 0.007 times 9E16 equals 6.3 e to the positive 13, which would be written as 6.3 times 10 to the 13th, and this is energy, so we measure it in joules. That's it. Now, I'm not here to gauge your faces to see how well you're understanding this. This may seem complicated, but let's go back and see another problem and work through it. Okay. How much mass is needed to produce 1.26 times 10 to the 14th joules of energy? This question is much simpler. So here's what we know. We know we have our E is equal to 1.26 times 10 to the 14 joules, right? We're looking for the mass because it says how much mass, and we know C is equal to 3 times 10 to the 8th meters per second. All right, let me double check, make sure I'm still recording. Good. Okay, so our equation is E equals m times c squared. All right, we plug in our E, 1.26 times 10 to the 14th. Okay, that equals our mass, which is I don't know, times our C, which is 3 times 10 to the 8th squared. Okay, so we know 3 times 10 to the 8th squared is 9 times 10 to the 16th. We've seen it a bunch of times. If you don't remember, you can always go back to your calculator here. Okay. We clear this out. All clear. 3 EE 8. And if you want to raise something to an exponent, you hit this x to the y. Boom. That gives you a little box right here, and you square it times 2. Hit enter. That is 9 times 10 to the 16th. Right? So that's how we got that number. Okay, so we bring this down. 1.26 times 10 to the 14th equals m times 9 times 10 to the 16th. And we want to get m by itself. So this is multiplication. So we just do the opposite. We divide both sides, 9 times 10 to the 16th. Divide this side by 9 times 10 to the 16th. Okay? These cancel out. Anything divided by itself is 1. And this gives us 1.26 times 10 to the 14th divided by 9 times 10 to the 16th. This sounds complicated, but this is the exact same thing as saying 6 divided by 2. These are just really, really big numbers. So in order to answer this question, I'm going to leave this up here. We just need to divide this number by this number. So, go back to our calculator. I know this is tricky because you don't have your handheld calculators. But this is what we need to do. 1.26 times 10 to the 14th divided by 9 times 10 to the 16th. Okay? So I'm going to clear this, even though that's the number we want. All right. So we're going to go 1.24 exponent, right? This is our exponent, the 14. Okay? 1/4 divided by 9 exponent, right, times 10 to the 16th. Equals, and their answer is 0.0013, or rounded up to 0.0014, which could also be 1.4 times 10 to the -3 kilograms. That's it. All right. Let me see if I have one more problem in here. All right, so let's solve. All right, so again, this is another problem So it says you have 7 kilograms of hydrogen fused to form 5 kilograms of helium and 0.4 kilograms of positrons. How much energy was released? Well, if we started off with 7 kilograms, okay, and we ended up with 5 plus 0.4, that means we started with 7, we have to subtract 5.4 kilograms, which means we lost a total of 1.6 kilograms, right? You started off with 7 kilograms, you ended up with 5 plus 0.4, 7 minus 5 plus 0.4 equals 1.6. Okay, so we know our mass is 1.6 kilograms. That's how much mass was lost, meaning that's how much mass was converted into pure energy. We're looking for how much energy there is, and we know c, again, is the speed of light, which is 3 times 10 to the 8th meters per second. So, plug our numbers in. This gives us E equals our mass, 1.6, times C squared, right? E equals mc squared. Our E is I don't know, our m is 1.6, and our c squared is 3 times 10 to the 8th squared, all right? Go back. Here we go. Okay, we clear this out. And all we need to do to find this is E equals 1.6 times 3 times 10 to the 8th squared. So, here's what we do. 1.6 times, I'm going to put this in parentheses, 3 exponent 8, and then I'm going to go to the, okay, squared. 3 times 10 to the 8th squared, close parentheses. You could have put in 1.6 times 9e16. That also works. It's the exact same thing. And then you just hit equals. Oh no. Can I get rid of this? There we go. That gives us 1.44 times 10 to the 17th. E to the positive 17. So this is our E equals 1.44 times 10 to the 17th joules. All right. Again, I understand that this involves using the calculator and working with these exponents. I understand that that can seem a little tricky, but I will be available on Zoom if you need help with this. Go back, rewatch the video, work through this with me. I think I explained everything that you need to know. If you are curious about nuclear physics in any sort of way, here is a list of videos that'll absolutely blow your mind. Okay, if you want to talk about mass, energy, and Einstein, if you want to talk about space-time illusion and time travel, things like that, give these videos a watch, talk to me about them. And yeah, that's it for this week. I know this video is a little long because I tried to cover as much as I could. Your DOL is, there's only a couple of math problems, but if you sit down and work them out, okay, I promise you, you can do this. I promise you, okay? All right, guys, have a great week. Find me on Zoom if you have questions. I hope you guys are happy and healthy, and I'll see you next week.